Hello everybody, welcome to the second lesson on the topic of vectors for the Year 12 portion of the course. In this session we're going to have a look at how we can represent vectors differently in both column vector form and in unit vector form, and we're also going to have a look at some vector arithmetic, adding, subtracting, multiplying with vectors. So before we start proper, here's a warm-up for 4 questions to have a go at. 1, 2, 3, 4. So try these first on your own, press pause now and attempt them independently of the video's help, then press play when you're ready to see the actual solutions and to check if you've got them correct. Okay, so let's have a look now at question 1. So question 1 says we have a diagram showing the vectors a, b, c and d, and given that a can be written as a column vector 2, minus 3, write the vectors b, c and d as column vectors in the space provided. So for this one, what we need to consider is the scale of this diagram. So we're told what A is. A is 2, 3, so we can write this in already. So A is 2, 3. So what this means is 2 to the right and 3 down. So each one of these big squares must be 1 unit. 1, 2 to the right, 1, 2, 3 big squares down, relating to this 2 and the minus 3. So, although I've put A here, we don't need to do A again, so I'm just going to focus on B, C and D really. So B, we're just going 1, 2, 3, 4 to the right, sorry 4 to the left, don't know my left from my right, 4 to the left, so it's minus 4, the top number, and we're going 1 unit up, so it's minus 4, positive 1. For C, the top number is 0, because we're not going left or right. The only thing we're doing for C is just going 2 units straight down. So it's 0, minus 2. And for D, we're going 1 unit to the left, so it's minus 1. And because we're not going up or down, there's no vertical movement, the bottom number is 0. And that's all we need to do for question 1. Question 2. We have a diagram showing 2 parallel vectors P and Q. We need to write each as a column vector. And so we can use the same scale as before, where 1 big square means 1 unit. So if we can see for P, now to write a vector, we can just simply write it as a letter with a line underneath to denote vector. So for P, we're going 2 to the right and 3 up. So P is 2, 3. And Q, we're going 1, 2, 3, 4 to the right, and we're going 1, 2, 3, 4, 5, 6 up, so it's going to be 4, 6. And if you note here, just note this for a second, we can note that actually, for this one, that Q is a multiple of P. Q is double P, so Q is 2 lots of P. And that's always the case when you have 2 vectors that are parallel. One can be expressed as a multiple of the other. And we're going to see this again in this lesson. So part B of this question. Put a circle around each of the following column vectors which are parallel to one another. Well, if you notice 2 and minus 1, if that were multiplied by negative 1, then negative 1 multiplied by 2 would be minus 2, and minus 1 multiplied by minus 1 would give us 1. And so if we multiply 2 minus 1 by a constant value, in this case minus 1, we end up with minus 2, 1, which is a vector we already have. And so this goes back to what I've just said. If one vector is a scalar multiple, just a multiple of a number of another, those 2 vectors are parallel. So because minus 2, 1 is minus 1 multiplied by 2 minus 1, these 2 must be parallel. And so the 2 we put a ring around are this one here and minus 2, 1 in the top right corner, because this one is a multiple of that one. To go from one to the other, we just multiply by the scalar value minus 1. Question 3. Some polynomial division revision. Divide x squared plus 5x plus 3 by x minus 1. So first we need to set out this correctly. Remember how to do so. So what we're dividing by, we put on the outside. What we're dividing, we put on the inside. Like so. So first of all, we take the highest power of x in the divisor and divide that into the highest power of x in the dividend. So we do x squared divided by x, which gives us x. So this minus 1 at this step, we just ignore. We're just dividing powers of x by powers of x in the divisor. The second step now is to multiply what we've just put down with the divisor. So we're going to multiply x by x minus 1. So that gives us x squared minus x. So now what we do is we subtract this line from the line above it. So x squared minus x squared cancels. That will always be true. 5x minus x is 5x plus 6x plus x, which gives us 6x. And before we repeat the process, we need to remember to bring down the next value along to this line. And now we go again. So now we divide 6x plus 3, the highest power of x here, 6x, by the highest power in divisor. So we do 6x divided by x minus 1. So 6x divided by x gives us positive 6. We now multiply the 6 by the x minus 1 on the outside. So 6 multiplied by x gives us 6x, and 6 multiplied by minus 1 gives minus 6. We then subtract. So 6x minus 6x cancels. 3 minus minus 6 leaves us with 9. There are no other numbers to bring down, and so we're now done. So 9 is our remainder. And so putting these pieces together, we can say that therefore x squared plus 5x plus 3 divided by x minus 1 gives us the quotient x plus 6 plus a remainder of 9, which is written as 9 over the same divisor, x minus 1. So that's all we need to do for question 3. Now let's have a look at question 4. So question 4 says, the data below shows a set of 10 scores in a multiple choice quiz. The quiz was marked out of 100, so we have these scores below. For part A, it says clean the data by circling any anomalies and eliminating them from the data set. So an anomaly is a fancy word, which I just need to explain to you what it means. All an anomaly means in plain English is an error or a mistake. So an outlier is an extremish value, a value which is quite a bit outside the range of the interquartile range. An anomaly is different to it. An anomaly is something which is just a mistake altogether. So an outlier might be unusual, but is actually valid. For example, a height of 6'8" would be an outlier. It's very, very tall, but it's possible. A height of 20 foot tall for a human being would be a mistake, because no human being can be quite that tall. In fact, no human being can be anywhere near that tall, I should say. So anyway, part A. Which one of these, or which ones of these, might be a mistake? So it's a quiz marked out of 100. 1 out of 100, that's very bad. That's a terrible result, but it's possible. Somebody might have got 1 out of 100, so we assume that to be true. All these look to be true. But if you see here, 102 out of 100, that has to be a mistake. And so we clean the data by circling 102 and then eliminating it. So the cleaned data is now all the data values that remain which weren't anomalies. So we just rewrite everything here In fact, you could have just scribbled this one off for speed. But I'm going to rewrite everything here apart from the anomaly, being sure to write both 47s. Then part B, we need to identify all outliers, and we can assume Tukey's definition of an outlier here. So assume an outlier to be an observation that falls either more than 1.5 times the interquartile range above the upper quartile, or more than 1.5 multiplied by the interquartile range below the lower quartile. And so for this, I'm going to show you how to use the class whiz to do the hard work for you. I'll also show you how to do it manually in case you're interested. So I'll show you how to do it manually, and then I'll show you the class whiz way. So this is a discrete data set. These values aren't continuous, they're certain. You get either a mark of 1 or 2 or 3. So for discrete data, first of all what we're going to do is find the median. And so working in from end to end, so it's not going to be the end values, not 40, not 47, not 42, or this 47. We can then see that the median value will be Q2. Now what we do is we ignore the middle and we think about the upmost end as a wing of the data. So we've got 4 data points in this upper wing. We now find the median of the upper wing. So halfway along this data line of 4 values would be halfway between this 47 and 48. So what this tells us here is that Q3, the upper quartile, would be halfway between 47 and 48. So Q3, the upper quartile, is going to be 47.5, because that's the mean of 47 and 48. In the same way, we take the lower wing, ignoring the median, and see that there are 4 values at the lower end. We now find the median of these 4 lower values. So halfway between these 4 lower values is going to be halfway between the second and the third value, which is here. So that's going to be where Q1, the lower quartile, is. Halfway between 38 and 40 is 39. Now I'm not recommending you do that way. I just want to show you so that the numbers don't look like witchcraft when the class whiz just generates them without any explanation. So how do you do this using the class whiz? I'll show you here. So we get the class whiz up and ready. We press menu and scroll along until we get to statistics and press equals. We want a 1 variable calculation, so press 1 for 1 variable. Now we just type in the data as it appears, pressing equals each time. So 1 equals 38, then equals 40, equals 42, 44, 47, press that one twice, because there's 2 47s, 48, and 49. Whoops, not 49, sorry, 99. So toggle back, 99. So press equals. Once you put all the data points in, which I now have, we press AC and clear away the data. Next we press OPTN, option, and option to 1 variable calc. We then scroll down and see that Q1 is 39, like we had here, and Q3 is indeed 47.5. So now we know this, we can now work out the interquartile range. So for part B, because Q3 is 47.5 and Q1 is 39, we can therefore say that the interquartile range is going to be 47.5 minus 39. You may as well check this with a calculator, but it's going to be 8.5. Now, the value mentioned here a lot is 1.5 multiplied by the interquartile range. So we can now work out, I'd suggest, 1.5 multiplied by the interquartile range. So 8.5 multiplied by 1.5, go back to the class whiz, press menu, so AC, then menu 1 for normal mode, 1.5 multiplied by 8.5 gives us 12.75. So, anything that falls more than 12.75 above the upper quartile is going to be an outlier. So the upper quartile was 47.5. So 47.5 plus 12.75. Let's see what this gives us. That gives us 60.25. And the lower quartile, which is 39 minus 12.75. That's going to give us as we can see here, 26.25. So we're after these values which are either less than 26.25. So anything less than 26.25 is an outlier. And so outliers, we have 1, or anything more than 60.25. So if anyone more than 60.25 is 99. So therefore we just conclude by saying that 1 and 99 are outliers. So not a hard question, but quite lengthy. But that's all we need to do for question 4, and that concludes our warm-up. So now we can get on to the main portion of the lesson. So let's have a look at that. Representing vectors. A vector can be represented by its change in position or displacement relative to the x and y axes. So this diagram to the right shows a vector A as a column vector. So A is 3, 4. So in other words, this resultant A can be considered as the overall movement of going 3 to the right and 4 up. This positive value is how far the vector moves in the positive x direction, and the bottom number tells us how far the vector is moving in the positive y direction. Addition and subtraction. So to add or subtract two column vectors, it's really straightforward. We just simply add or subtract the x components and the y components respectively. So p, q plus r, s, we just add the tops. P plus R is P plus R, and we have the bottoms respectively as well. So Q plus S is Q plus S. Or if we're multiplying by a scalar. Now a scalar is just a constant number, like 3, 4, 5, pi, 9.9, whatever. So how to multiply by a scalar? To multiply a column vector by a scalar, call it this Greek symbol lambda, we just multiply each component by the scalar value lambda. So lambda lots of p and q is lambda times p at the top, and then lambda times q at the bottom. So let's have a look at a quick worked example now, using this idea of column vectors. So for part A, how to work out 1/3 of A. Well, 1/3 of A just means 1/3 of 2 and 6. So 1/3 is for scalar, so we just multiply 1/3 by the 2, and then multiply 1/3 by the 6 separately. So 1/3 multiplied by 2 is 2/3, and 1/3 multiplied by 6, 1/3 of 6, if you like, is 2. And so that's it for part A. For part B, the vector A plus B is the column vector 2, 6, plus the column vector 3, minus 1. So we add the tops, so 2 plus 3 is 5. That's meant to be a 6, looks like a B. 6 plus minus 1, again, is 5. And that's it for part B. Finally, for C, we have 2A minus 3B to work out. And so 2 lots of A is 2 lots of 2, 6, minus 3 lots of B, where B is 3, negative 1. So 2 lots of 2, 6. Do the top number first. 2 times 2 gives us 4. 2 times 6 gives us 12. Then we're going to minus 3 times 3, which is 9. Then minus 3 multiplied by minus 1. That's actually going to give us a positive 3. But of course, if we're subtracting a negative, we're actually going to be adding it in a sense. So we're going to think of this as 3 multiplied by minus 1, which is minus 3. So one way of thinking about it is we're leaving this negative alone and just multiplying both of these by 3. 3 times 3 is 9. 3 times minus 1 is minus 3. We can now go ahead and add. So subtract. 4 minus 9 is minus 5. 12 minus minus 3 is the same as 12 plus 3, which gives us 15. So that's all we need to do for that particular worked example. Let's just go forward now and think about how we can use unit vectors to represent vectors in 2 dimensions. So a unit vector is a vector length of 1. So a unit vector is defined of length 1, no matter what direction it goes in. The main unit vectors, though, the main sort of elementary unit vectors, go along the x-axis and y-axis. And these are denoted by I, which is 1 unit in the positive x direction, and j, which is defined as 1 unit directly upwards, in other words, 1 unit in the positive y direction. So this diagram will illustrate this. So as you can see, I is 1 unit to the right, no units up or down, whereas j is no units to the left or right, but is just 1 unit and only 1 unit precisely going upwards. So we can consider any 2-dimensional vector in the form pi plus qj. So just consider this triangle shown to the right. Imagine you've got this vector 5i going to the right, 5 units, and 2j going upwards by 2 units. Then we can consider a to c, the vector going from a to c, as the resultant of 5i and 2j. So by the triangle law of vector addition, the vector AC is a vector AB plus BC. So it's just literally 5i plus 2j. It's 5i and 2j. You can also write this, if you wanted to, as a column vector. So 5i plus 2j is 5 to the right, so the top numbers are 5, and 2 units up, so the bottom number in the column vector is a 2. Generally speaking, for any 2-dimensional vector, the column vector PQ means P units to the positive x direction plus Q units in the positive y direction. PQ equals PI plus Q lots of j. So here we've got a worked example just going through this with a bit more depth. So define A as 3i minus 4j and B as 2i plus 7j. First of all, we need to find half A. So for part A, finding half A, half of A is just simply half of whatever 3A minus 4J halved is. So we're just going to expand these brackets in the same way you would with basic algebra. So half times 3I, that's going to be 3 over 2I. Then half multiplied by minus 4J is going to be minus 2J. And that's all there is to it. For part B, A plus B in unit vector notation, well, we have A, which is 3I minus 4J. I'm going to add to that B, which is 2I plus 7J. So all we're doing here is just replacing the vector A with how it's denoted in its unit vector form. And B in unit vector form is 2I plus 7J. So now what we do is we just think about looking at the I components first. So 3I plus 2I, overall that's going to give us 5I. And the J components, minus 4J's plus 7J, gives us plus 3J overall. So at this stage, it's very much just like simplifying basic algebra. Simplify the I's, collect your like terms, and group together the J's, collect your like terms in the same way. For part C, we need to work out 3A minus 2B, again in unit vector notation. So 3A, we need 3 lots of 3I minus 4J. Then we're going to subtract 2 lots of B, which is 2 lots of 2I plus 7J. So 3 times 3I is 9I. 3 times minus 4J gives us minus 12J. Then minus 2 times 2I is minus 4I. Minus 2 multiplied by 7J is minus 14J. Now collect like terms, collecting I components. 9I minus 4I gives us 5I. Then minus 12J minus 14J gives us overall minus 26J. So although the concept of vectors may seem quite complicated and abstract, it's very much like simplifying the algebra you've seen from earlier in the course. So there's nothing to be nervous about, it's just applying the old rules in a new context. Let's take a look at another worked example. Example 2. So given that A is 2I plus 5J, B is 12I minus 12I minus 10J, and C is minus 3I plus 9J, find A plus B plus C using column vector notation in your working. So this is actually quite straightforward. So column vector notation, personally I think column vectors are easier. So A plus B plus C, column vectors, so A is 2I plus 5J. So we just write 2, 5. Plus B, B is 12 minus 10. And then C is just going to be minus 3 at the top, 9 at the bottom. So all we've done here, just converted them from one form to the other. So A, which is that, we just write in column vector form. B, which is this, we write as such. And C, exactly the same way, we just write like this. So that's just a case of adding the top numbers together, then the bottom numbers separately. So 2 plus 12 minus 3. 2 plus 12 is 14, plus minus 3, in other words take 3, 14 take 3 is 11. For bottom numbers, 5 plus minus 10. So 5 minus 10 is minus 5. Minus 5 plus 9 gives us 4. So A plus B plus C in column vector form is 11, 4. Alright, so questions 3 and 4 are slightly harder worked examples. We're going to boil down actually to doing simultaneous equations. So question 3, we're told that vector A is 2i plus 3j and vector B is 7i minus 2j. Find omega, which is this fancy W looking symbol, if vector A plus omega B is parallel to minus 12i plus 7j. So this goes back to what we said in the warm-up. So if two vectors are parallel, in other words, this one and that one, then one could be expressed as a multiple of the other. So what we can say here is that A plus omega B is equal to some multiple, let's call it lambda. You could call it whatever you want within reason, as long as there's not any swear words or something. You can call it lambda, then brackets, minus 12i plus 7j. So it's actually easier to see when we write it in column vector notation. And so let's transfer this to column vector form. So A is 2, 3, plus omega lots of B, where B is 7 minus 2, equals lambda, minus 12 on top and 7 on the bottom. Now if we just take this as top numbers first, horizontal components first if you like, so 2 plus 7 omega equals lambda multiplied by minus 12. So that's going to equal minus 12 lambda. Then looking at the bottom numbers, 3 omega times minus 2 gives us minus 2 omega equals lambda times 7. In other words, that's 7 lambda. So actually what we've got here is two simultaneous equations which we can solve. So what we could do here is try to eliminate lambda, because we're not interested in lambda, we're actually interested in this omega. So we need to get rid of lambda. The signs of lambda at the top and bottom are different, so if we add them in some multiples, they should disappear. So what's the lowest common multiple of 7 and 12? Well, with a bit of working out or using a calculator, that's going to be 84. So what we could do is multiply the entirety of the top equation by 7 and multiply all of the bottom equation by 12. And if we do that, multiplying everything on the top by 7, we'll get 14 plus 49 omega equals minus 84 lambda. And on the bottom, 3 times 12 gives us 36. Minus 2 omega multiplied by 12 is minus 24 omega. And 7 multiplied by 12 gives 84 lambda. Now, if we add these equations together, we'll get these lambdas cancelling, which is what we want. So 14 plus 36 is 50. 49 omega add negative 24 omega is the same as 49 omega minus 24 omega, which is minus 25, sorry, plus 25 omega, equals 0. So now we can take this and fairly easily rearrange it. So subtract 50 from both sides gives us 25 omega equals negative 50. Divide through by 25. We therefore see that omega must equal minus 2, which is what we wanted to find all along. Question 4, a two-parter. So we've got the resultant of two vectors to consider. So the resultant of vectors A, where A is 3i minus 8j, and b, which is minus 3pi plus 2pj, is parallel to vector c, where c is minus 3i plus j. First of all, we need to find the value of p, and secondly, the resultant of a and b, giving the answer as a column vector. So the resultant of a and b is going to be a plus b added together. So we may as well just write this down. Resultant of a and b, that's just going to equal a plus b. So a is 3i minus 8j, so 3 minus 8, plus b, which is minus 3p at the top and 2p at the bottom, gives us, adding the top bits, 3 plus minus 3p, that's 3 minus 3p, and the bottom numbers, minus 8 plus 2p on the bottom. So this is parallel to the vector c. Okay, so the resultant of a and b, which we just worked out is this, is parallel to c. So we can now say, because the resultant of a and b is parallel to c, then this implies that the resultant of a and b, which is 3 minus 3p on top, minus 8 plus 2p on the bottom, is some scalar multiple, let's again call it lambda, some multiple of c, which is minus 3 on top, 1j, so 1 on the bottom. So in other words, the resultant of a and b is some multiple of c, where c is in vector, column vector form, minus 3, 1. So we can now generate simultaneous equations from this. So looking at the tops, we have 3 minus 3p must equal minus 3 lambda, and on the bottom, minus 8 plus 2p must equal lambda multiplied by 1, which is just lambda. So we don't really want lambda, we're not interested in lambda, we're interested in p. We can eliminate lambda by taking the bottom equation and multiplying it all by 3, and then adding both top and bottom equations together. So if we leave this one as it is, so we have 3 minus 3p equals minus 3 lambda. The bottom, if you multiply everything by 3, is going to become minus 24 plus 6p equals 3 lambda. We can now add these two together. And what we get when we do that is 3 plus negative 24, that's minus 21, minus 3p plus 6p, that's plus 3p, and these lambdas cancel. Minus 3 lambda plus 3 lambda is 0. So minus 21 plus 3p equals 0. A bit of simple rearrangement should tell you that therefore p must equal 7. And that's part A complete. P has to equal 7. Now part B is much easier. So now we know P, we can work out the resultant of A and B. So the resultant of A and B, we worked out was this. Resultant of A and B was 8 minus 3p and minus 8 plus 2p on the bottom. However, because you know now p is 7, we can just sub in p being 7. So this becomes 8 minus 21, because 3 times 7 is 21. And sorry, what have I said? This is not 8, it's 3. Another mistake yet again here. Slack. I'll leave it in, just so you can see what a buffoon I can be. I do apologise. Sorry, this is meant to be a 3. What am I thinking? I do apologise if this has got you thinking, what is he talking about? But I'm not vain. I've got no illusions, but I do make lots of mistakes. So I will keep this in. So 3 minus 3p becomes 3 minus 21. And at the bottom, minus 8 plus 2p. P is 7, so 2p is going to be 14. So if we just simplify and work out these calculations, 3 minus 21, that gives us minus 18. And minus 8 plus 14, that gives us 6. And that's the final answer and concludes the session. So now it's over to you lot. So if you could turn to page 238 in the blue algebra books, that's exercise 11b, and try this selection of questions. So question 2, A, C, E, G. Question 3, parts B, D and F. Then question 4 all the way through to question 10. Being careful and mindful to check your answers as you go, and also always asking me if you're getting stuck at any point. So happy hunting, do practice hard, and I'll see you very soon indeed. Thanks for listening. Remember to subscribe if you can, and I'll see you in lessons in a jiffy. Thank you for now. Bye.